So example, if we have two parallel plates and we want to find the strength of electric field. So between the two parallel plates, you can see here the distance between the field lines is same. So it means electric field strength is constant. How the electric field strength is constant, you can simply understand from if we have two plates which have unlike charges, one is positive and the other one is negative. The resultant force is same throughout this between the plates. Example, if there is one charge, example, there is a positive charge which is exactly placed at the center. So what happened? The negative plate will attract and the positive plate will repel. So at the center, if the force exerted by the positive plate was 50 and the force exerted by the negative plate is 50, what is the resultant force here? The resultant force, because it is in the same direction, so the resultant force will be 100 newtons at the center. But if I move this positive charge near the positive plate, so as I move this near the positive plate, so it shows that it will have, this will show that this will have more repulsion and less attraction because it is closer to the positive plate. So less repulsion will be there. So repulsion force, example 25, less attraction, more repulsion. So example attraction force is 25, and because it is closer to the positive charge plate, so there is more repulsion. So example the repulsion is 75. So when I find the resultant force, so 25 plus 7, because both forces are in the same direction, so resultant what I will get? I will get 100 Newton. So same way, if I take any point within this field, what I will observe? I'll observe that the force from the positive plate will decrease, force from negative plate will increase, but the resultant force at any point will remain same. And the formula for electric field strength, we have E is equals to F over Q. So force, the resultant force is not changing. Q is the charge that is constant. So what will happen? Strength of the electric field is also constant. So between the plates, the strength of electric field does not change for the test positive charge. For the two parallel plates which have charge between the plate. Is it clear?
Yes, sir.
And how we can find a formula which can be used to find this value of the electric field between the plates. So electric field strength is equals to voltage divided by distance between the two plates. So E is equals to V divided by D, where V is the potential difference and D is the distance between the plates. So what can be the another unit for electric field strength? The other unit for electric field strength, V is the voltage and D is the distance. So it can be, voltage is volts and distance is meter. So it can be volt per meter. Is it clear? So copy this part. Electric field between the parallel plate capacitor or parallel charge plates. So if we have a hollow charge, what's the meaning of hollow charge? It means like you have a sphere and the surface of the sphere is charged. And in this example, it is positively charged, as you can identify that the field lines are pointing out. So inside there is no charge. So the net electric field is strength inside the hollow charge is zero. There is no, if I place a charge, like example, if I place electron, this electron will not move anywhere due to the electric field strength because inside there is no electric field strength. But if I place electron outside, then this electron is attracted. So for a hollow charge sphere, the net field strength inside a hollow charge sphere is 0. But for outside, it will behave like a charge created at its. So the field behave as if all the charge created, it is at a point in the center of the sphere. Like it will generate electric field and it will appear, this is only appearance, that it appear that there is a point which is generating the electric field and that charge is exactly at the center of the hollow sphere. This is what will appear. But in reality, what happened if a metal sphere is charged metal sphere, either positive or negative, so on the surface there is a charge. So how the electric field lines we will draw? We will only draw the field lines on the surface. And what it appear, it only looks like that there is charge inside, it looks like only, and that is creating all the electric field. But in reality, only charge is there at the surface, and within the hollow sphere, inside the hollow sphere, there is no electric field lines, there are no electric field lines, and there is no electric force present or experienced by the charges. Is it clear? The hollow charge sphere.
Yes, sir. Clear.
Okay. Copy this as well and the figure. Now, if we sketch a graph for electric field strength, for a point charge, for a parallel plate capacitor, and for a hollow charge, what will be the shape of the graph? First thing, for a point charge, the formula which we use for finding the electric field strength of a point charge, that formula E is equals to K, capital Q over R square. K is a constant, Q is a constant, so means the variation is due to R. So if you have a point charge, say electron is there, and you want to find the relation with it as you move away from the electron, how the electric field will vary. So as you can see, electric field is inversely proportional to R square, but inverse is square. Means if I multiply a distance, if I double the distance, electric field will decrease by 4. If I triple the distance, electric field will decrease by 9. So it follow inverse square law. That's why whenever two values are curved, having a curvature, then it is exponential change. Like when inverse square law is there, the graph will be a curve and shows a greater change or variation. That's why for electric field strength versus a distance, this is for a point charge. That's the first one. If you have parallel plate, just now I explained to you the parallel plates as for a parallel plates, for any kind of, for unlike plates here, what happened? The electric force is constant and E is equals to F over Q. So E is equals to our electric field strength is equals to force divided by charge. So what happened? Q is constant. We place any small q, that's constant. But what about force? That is also constant. I just give you an example. If you move this charge at any point, the forces from positive and negative plate will change, but the resultant force will be same. If resultant force is constant, Q is constant, so always E will remain constant or E will not change. So you can see here, it will always be a straight line. And E is also having a formula V over D. So we can also say V over D will not change. Is it clear, the second graph for a parallel plate?
Yes, sir.
And for third one, as we just now discussed, for a hollow sphere, inside the sphere, there is no electric field. So till this point, the electric field is zero. It means within the sphere. Once you reach the surface, then it will vary like a point charge. So it will vary like a point charge. So these are the three shapes of electric field which you will observe if there is a point charge, if there is a parallel plate capacitor, or two metal plates are there, and if there is a hollow charge. Copy this, sketch the graph. Then what is electric potential? Electric potential, it is a work done on a unit positive charge from infinity to that specific point. For example, if you have a charge object, so this is a charge object, it can be positive or it can be negative. So how much work is done on a unit positive charge? So there's a unit positive charge and it is far away from the charge, or it is infinity, at infinity. And we move this from infinity to a certain point in the electric field. So how much work we did, like example, I did a work done of 30 joules. So what is the electric potential? The electric potential is refers to 30 joules. So work done on a unit charge to move the charge from infinity to that point or to specific point within the electric field. Is it clear, the concept of electric potential? That's also called voltage. So how much work you did, like example, you applied a force of 30 Newton and you move this charge 1 meter. So how much work is done on this charge? So 30 Newton force multiplied by 1 meter. So 30 multiplied by 1, work done is 30 joules. So 30 joules is a work done, or electric potential is joules per coulomb, like for each. So how much work is done? 30 joule divided by the charge example was 1 coulomb. So 30 joules per coulomb, which is also known as electric potential. At infinity, the potential of a charge at infinity is always zero, because at infinity we don't have to apply a force, like we don't have to do any work done, because it is not experiencing any force. So if force is zero, the work done will be zero. If work done is zero, it means the electric potential is zero. So using this concept of electric potential, we also define equipotential surface. Like example, a charge is at position A and I move the charge, I did a work done of 30 joules. So using a work done of 30 joules, what I can do, I can move this charge to different points where I'm doing a work done of 30 joules. So many points are there where I'm doing a work done of 30 joules. So if I join these points, when I join these points where a same work is done, that line which represent the work done is same for all the points, that line is known as equipotential. Equi means same and potential means voltage. So that line is refers to equipotential surface. Is it clear?
Yes.
So
Yes.
copy electric potential. Then next slide you will find equipotential surface as well. So here you can see the equipotential and the electric field. Basically, the gradient of electric potential is known as the electric field strength. And what are equipotential surfaces? Equipotential surfaces are refers to the lines which represent the same work done. Are like example, if an object or a charge is at point A and we did a work done of say 30 joules. So these all surfaces are representing like these all surfaces are representing the equipotential, means the same potential difference between them. If moving from one, like this is surface 1, 2, 3. So moving from surface 1 to surface 2, if the work done is 30 joule, the moving from surface 2 to surface 3 is also. So moving from surface 2 to surface 3 is also same. But you can see the distance between the equipotential surfaces is decreasing. Like, what is the reason for that? If we are at position on surface 1 and we move from surface 1 to surface 2 and we did a work done of 30 joules. So work done, voltages were and equipotential voltage is work done per unit charge. Charge is not changing. So work done is force into distance divided by charge. So what happened when the charge is away from the source? So what happened? It will experience a smaller force. So if it will experience smaller force, for the same energy, you can move the charge to a greater distance. But as the charge is closer, so the force increases. If the force increase, the distance, the work done, for the same work done, if I have a greater force, so then I can move a charge to a smaller distance. So that's why what you'll observe as you are moving closer to the source of the electric field, you will find the distance between the equipotential surfaces is decreasing. Is it clear?
Yes.
Yes, sir.
Okay. Copy this.